Good morning. I'd like to start out by thanking Mohan and the organizers for inviting me here today. This is quite an honor, and I can't emphasize how important the work that you all do is to our program. I guess to start out with my credentials, I'm an electrical engineer by training and was president of my student chapter at the University of Buffalo a very long time ago. And in that, I'd like to mention there are many opportunities, before I get into my speech, for the students and the IEEE to get involved with our activities. Each summer, all the modal agencies at the Department of Transportation run intern programs. Usually the advertisement goes out in January to February for summer intern opportunities. With the recent unintended acceleration activities going on in the automotive industry, the Department of Transportation, and NHTSA in particular, is starting an electrical engineering safety center, which we should start staffing up this August. So there are many opportunities that we already have the tools in place to support active involvement with the IEEE and its members. Excuse me. To begin, I don't expect to be able to come here today and wow you with advancements in technology and our capabilities because what we do leverages what you do. And really the focus of my talk today is to talk about how the work that everyone in this room and in this community is doing and how it's getting implemented today to support our mission. Now, I work for the National Highway Traffic Safety Administration. It's an agency of the U.S. Department of Transportation, and our sole mission is to reduce death, injuries, and the economic loss resulting from motor vehicle crashes. We do that in two ways. We try to influence driver behavior. We've been wildly successful in getting drivers in the United States to start wearing their safety belts, and we've greatly reduced the incidence of alcohol-impaired driving through a bunch of driver behavior programs. Now, the part of the agency that I work at is focused on vehicle safety, and we're the regulators. I don't typically introduce myself as, hi, I'm a regulator. It's not a good way to make friends. But the work we do is trying to identify if does technology solve a problem, and if it does, what can the government do to get it deployed. And everything we do is focused on the problem. We don't come at it looking at technology and then looking for a problem for it to solve. In the United States, traffic fatalities have been going down. This past year was a record year. We had almost 34,000 fatalities this year. That's still a lot of people the size of a small city, but it's way down from 55,000 that we had in the 1950s, and then we plateaued at 40,000 for about 10 years. But between reduction in miles driven and the increases in automotive technology and driver behavior, we're seeing this great reduction. Nonetheless, we're seeing car and heavy vehicle crashes and fatalities go down. Motorcycle fatalities are spiking up. This number would be even lower if we could get a handle on the motorcycle problem. It's the leading cause of death for all ages from 4 to 34, and it's in the top 10 for all ages. On top of that, this technology addresses the mobility problem. Mobility is only getting worse. The environmental and sustainability issues as well are a focus of this area. And ultimately, we think we have pushed crash worthiness, protecting the driver occupant. There's more that can be done, but we've really pushed that very far. The technology that the auto companies have implemented makes surviving a crash, gives you a much greater chance of doing that. However, we think the next step is to prevent that crash. And both vehicle-based technologies that are on the market today and new vehicle communications will enable that. I think an important point is when I started in this business, we were always talking about what we were going to do, what we could do, but today we sit here and you have done it. There's nothing on this page that isn't for sale. And these advanced crash avoidance systems are not only available on the high-end Mercedes-Benz, BMW, Cadillac. We're starting to see them filter all the way through the fleet. Very effective technologies such as electronic stability control, now that it's being required, are available up and down the entire fleet from the Chevy Cobalt all the way up to the most expensive vehicles. And we're starting to see things like adaptive cruise control, crash imminent braking on mid-range vehicles. And then we think when we get to vehicle communications, because of its reduced cost, that will spread throughout the entire fleet. So it's no longer just the state of the art, this is the state of the practice. And I can think of nothing we can do better for the American public than to get these safety systems out there. When we started in this business, the big issue were false alarms, false positives, were the crash avoidance, crash warning systems warning when there was no imminent threat, and more importantly, were they not warning when there was a threat. The cost of these systems was very high. We ran our first field operational test of an adaptive cruise control system in 1995. We put it on a Nissan Altima, which cost about $15,000. By the time you put the radar and other sensors on, it was a $100,000 vehicle. So obviously that's not affordable. But now we're seeing these radars are down to the hundreds of dollars, and the auto manufacturers are able to sell them as a viable product. And then finally, HMI, the human-machine interface, the driver-vehicle interface. Those of us who work in this area get very used to these systems, and we understand how they work. The American public, for the most part, is not aware of these systems. They're not aware of the technology. When they first hear about it, they seem to be very skeptical, but then when they've experienced it, they seem to fall in love with it. So getting the experience of the American public with these technologies, I think, has been critical. So we have been working at this from the government perspective since the 1980s. And by no means by this slide do I try and infer that the government pushed this technology forward. Probably the bulk of this development was done in private industry with the support of academia, and then the government did what it could to spur things along. In the 1980s, there was a group called Mobility 2000 that brought together really some advanced thinkers on what could we do to improve safety and mobility in the transportation sector. And out of that came the Intelligent Transportation Systems Program, and in particular, the Advanced Crash Avoidance Program that I've focused on. In the early 1990s, there's something called the Federal Trust Fund that funds highway programs and research programs. And ICE-T was the first one that started the ITS program and put big research dollars behind it. At that time, we started the Advanced Collision Avoidance Program and the Automated Highway Systems Program to demonstrate that these technologies did have the ability to solve these problems. We transitioned in the late 1990s under T21, which is our next funding in government. You live your life by when your next chunk of funding comes. And we transitioned from the AHS program, which looked viable but wasn't getting public acceptance, into the Intelligent Vehicle Initiative, where we really focused on getting crash warning and crash avoidance systems developed and tested out with the public. And that brings us to today, the Safety Lou program, where we're now supporting deployment of vehicle communication systems. And what did we get out of all of this? We've funded over 20 field operational tests where we put real vehicles, cars, transit vehicles, heavy trucks out on the road with crash warning systems, using real drivers out on public roads to understand, one, are the systems effective, and two, do the drivers accept it? And in each case, we've done this with navigation systems, crash warning systems, and situational awareness systems, and we've shown and demonstrated that these systems are effective. In most cases, the systems would actually get on the market and for sale before we'd actually finished our field operational tests completely voluntarily by the manufacturer. But that data gave the department the information it needed to support the deployment of these systems. Our first activity is called the New Car Assessment Program, and you might know this as the Stars on Cars program. Historically, it's been a crash rating program to rate how well a vehicle survives a crash. In this past year, we have extended it to identify crash worthiness systems and crash active safety systems that the government is confident in will improve safety. So before we went to regulation, we included the electronic stability control system. We included forward collision warning based on our field operational test results, which showed up to a 20% reduction in crashes. And we included lane departure warning systems, which we saw about a 10% reduction in run-off-the-road crashes from those systems. So in the next model year, if you go to the NCAP site, not only will you get information on the crash worthiness of a new vehicle, you'll also be able to identify which vehicles have these options available. And then moving a step forward, last January, we published our rulemaking priority plan. And this is the department's first step at advertising what areas we want to make regulations in. And we've included several active safety systems in this. Electronic stability control, that one already has gone to regulation, and that's in its phase-in period. That'll be required on all vehicles, light vehicles, over the next 5 years. And we're implementing a rule for heavy vehicles soon. We are in the research phase of making decisions on forward collision warning and crash imminent braking. We'll have that completed by next year, and at that time we'll announce if we're going to require that. Lane keeping assistance is in the same state. We'll make that announcement in 2013. Pedestrian collision avoidance, which is basically a derivative of crash imminent braking, that'll also be in 2013. And then finally, vehicle communications, particularly vehicle-to-vehicle communications for safety. We have an extensive research program underway with the automotive community, and we will announce if we're going to go to require that in 2013 as well. And what does it mean to go to regulation? NHTSA, as part of the Department of Transportation, has authority from Congress to establish the Federal Motor Vehicle Safety Standard, FMVSS. FMVSS is if we publish one of these, that equipment is required to be on the vehicle. If there is no FMVSS that covers that system, cup holders, it doesn't say you can't put it on there, so it leaves it open that you can. So right now, forward collision warning, most active safety systems can voluntarily be deployed by the vehicle manufacturer, but if there's an FMVSS in place, it has to be on there. And they have the force of law. If one is in place, the manufacturer has to comply with it. It only applies to new vehicles, not vehicles that are already out on the road. When any agency in the U.S. government passes a regulation, we're required to abide by the Administrative Procedures Act, which basically requires transparency and openness. We have to announce ahead of time what we're going to do, how we're going to do it. We have to take public comment. This typically happens in the Federal Register, and now there's a website, regulations.gov. And we have to respond to each and every one of those comments. All of that gets put in what's called a docket. It used to literally be a file cabinet in Washington, D.C. that anyone could go up and look in. But now this is all on regulations.gov. If you want to put in a comment, it goes out. Anybody can read it, and the government eventually will respond to that comment before we move forward with regulations. Within, particularly for NHTSA and the FMVSS, we have some a different set of standards that are more stringent. One, anything we do has to meet a safety need. So we do not set regulations for a system that improves mobility. Toll tags is not covered by us. And it has to be automotive equipment, not nomadic devices. We do not regulate cell phones. But something like a navigation system that is nomadic, but it's primarily meant to be in your car, that's considered automotive equipment. So NHTSA does have jurisdiction over that. Our technology has to be practicable. And what that means, it has to be technologically effective, it has to exist, and it has to be economical. There has to be a cost benefit. We are different from the EPA. The EPA can set standards on emissions, and then force the industry basically to create technology that meets that. Within the safety realm, we're not allowed to operate that way. Our standards have to be objectively measurable. So we have to be able to put out a specific test procedure with criteria that the vehicle manufacturer can then test his system and see if he meets it. We prefer to be performance-oriented as opposed to put out design guidelines. So for something like a forward collision warning system, we won't say you need to have a radar with a given aperture. We'll say you need to identify a threat within a given time frame and warn the driver at a certain time. And then we set standards by vehicle type. Rarely are they blanket standards. We set different ones for light vehicles, all the different classifications of heavy vehicles, motorcycles, and transit vehicles. Each get treated separately. And where do we decide? How do we decide what to make a rule on? It comes from all different areas. NHTSA research, NHTSA-sponsored research is one of the biggest areas. You can write in a letter to the government and ask for a regulation if you like. We get those all the time. We don't act on many of them. Harmonization is where we try and align with global technical regulations, the regulations that the government bodies in Europe and Asia are doing. Legislation, this is the fast-track way of doing it. When Congress tells us to pass a regulation, we pass a regulation. And then there's some sort of broad areas. All of ours are in the public interest. We look at compliance issues, such as the Toyota issue right now, or the Firestone tire problem that happened about 10 years ago, where the tire pressure monitoring systems were implemented in response to that. And technological changes. I think vehicle communications will be an example of that. And then the process is always the same. We have to do the research and development to create the data, initiate the data, put out a notice of proposed rulemaking. That's what goes into the Federal Register, receive your comments and respond, and then from that we can publish a final rule. Typically, the research and development stage can take a year to 20 years, as it has. But once we get moving on it, typically it's about a 3-year period, and then we often give up to a 5-year phase-in period for the manufacturers. Some large manufacturers that have multiple models, it takes them a while to be able to apply these technologies across their entire fleet. So given all that, we want to focus this capability on the IntelliDrive system, using vehicle communications for safety. And we think this can really help us take that final big push to get crash avoidance on vehicles. It does two things. It provides greater situational awareness with inexpensive radios compared to radars or other sensors. You have the ability to tell the driver about all the vehicles, pedestrians, other obstacles that are in a 360-degree area around his vehicle. And from that, we can reduce crashes by providing advisories, warnings, and ultimately vehicle control. In this context, we're talking about crash avoidance, braking or possibly even steering the vehicle momentarily. We're not talking about full automation, although this technology could support that. Our internal analysis has shown, if you look at all the crash types that occur from non-impaired drivers, not drunk drivers, we think we can attack about 76% of those with vehicle communications. A lot of the runoff road ones are single vehicle ones that vehicle communications won't help with. And also, and we're not trying to make better drunk drivers, so we're focused on the good population here. The benefits, we think, ultimately, the DSRC units can replace the more expensive onboard sensors. We are focused for vehicle communications exclusively on dedicated short-range communications, 802.11p, 5.9 gigahertz, because of the low latency and range requirements that we think we need to attack those 76% of crash problems. When you talk about vehicle communications, it's implied you also need to know where you are. So you require some type of positioning capability. With vehicle-to-vehicle, we think you can just use regular GPS, automotive-grade GPS, with relative positioning. We don't think you need enhanced GPS, which you would need for some of the vehicle-to-infrastructure applications that may come down the road, such as stop sign, signal violation warning. And then what we've heard from the automotive manufacturers, a great benefit of this is to offer most of the safety applications for vehicle-to-vehicle. you don't require a digital map, which can be a very expensive element to add to the system. So it brings down the cost as we increase the benefit. So that's why we think there's a great opportunity here. And this, we start to frame around the issue of cooperative versus vehicle-based systems. And when the government puts out a regulation, we have to put out a benefit cost estimate. And one of the things we have to do is not create lives when we do that, which the government has done in the past. So you can't recount a problem that you've already solved, such as electronic stability control is estimated that it'll save 20 to 50% of the run-off-the-road crashes. So we can't count those towards the benefit of vehicle communications because there's technology that will be out there that's already solving that problem. However, we've seen that because of our confidence in vehicle-based systems, a forward collision warning, lane departure warning, that gives us the same confidence that those applications can transition to vehicle communications and that the technology will be cheaper. The greatest drawback is the deployment issue. A vehicle-based system, if you pay for it, you have it on your car, you get the safety benefit. With vehicle-to-vehicle communications, we have to get it across the entire fleet as quickly as possible to drive up the benefits. Although we think at the 20% range, you'll start seeing benefits for the individual driver. So to make this happen, we've created a vehicle-to-vehicle research plan. And it may not be, these issues may not pop out to this group, but they were important in the transportation community of trying to focus our research plan. So the primary application of V2V is to enable safety applications. Initially, we're not looking at mobility applications or sustainability applications, but eventually we think if you have this vehicle communication capability, you can do these other things with it. V2V cannot be dependent on widespread deployment of infrastructure. The state departments of transportation are under incredible financial pressure right now. We cannot burden them with having to put out DSRC units at every traffic light in their jurisdiction, and then even past that, requiring them to maintain those systems. So we think V2V can get deployed without this massive publicly funded infrastructure. This system architecture needs to be compatible with evolutionary changes. One of the benefits, or what makes DSRC very attractive, is the stability of the technology, so that we know whatever we put out there is going to be out there for a long time. It has to be effective, but it has to be able to evolve when something better comes along. And finally, as I said before, we've looked at it. Of our available options today, DSRC at 5.9 is the only viable option. Things like 4G, 3G really don't have the latency to do the crash imminent applications that we're trying to do here. From that, we, within the department, have put together this suite of programs. I'm going to talk about the first couple today. There's more information on our IntelliDrive website. I'll give you the web address for that at the end of the presentation. But these pieces all fit together. We have vehicle-to-vehicle program is looking at developing the applications, addressing the interoperability issues. The safety pilot is looking at creating the model deployment to show this effective system. Human factors for IntelliDrive is looking at, well, now that you've created this Pandora's box of getting information into the car, how do you make sure we're not distracting the driver to make the situation worse than it already is? Policy, whether you're talking about vehicle-to-vehicle or vehicle-to-infrastructure, is just as important as the technology issues. There are more partners involved in this program than we've ever had before. You have the entire vehicle building community, you have the operators, and then you have the entire infrastructure community. So there are a lot of players in this game than we've ever had to deal with before. Vehicle to infrastructure is going to be a follow-on program looking at, once you have the cars outfitted, what can you do in the infrastructure to solve additional problems, such as at intersections. We have a across-the-board systems engineering program on board that supports all of these activities. And then we have an existing test bed in Michigan outside the Detroit area for helping other, not just government-sponsored research entities, but others, giving them a tool so they can exercise their capabilities as well. This is the vehicle-to-vehicle roadmap. This, we underwent a public meeting about a year ago. Out of that, we got basically favorable comments. We made a couple of changes. We added the policy. We had up to track 5 about a year ago, and then since then we added a specific track on the policy issues. And then we added special work on tracks 7 and 8 to specifically address the commercial or heavy vehicle community, which are basically going to use what comes out of the light vehicle program, but they need to modify it to their unique situation. And the same goes for the transit program. So I won't talk too much about those last 2 tracks anymore. So the V2V program, I'll quickly go through each of these tracks. So let me just skip over this slide. Track 1 is the crash scenario framework. As you saw when I talked about our regulatory requirements, we have to be solving a problem. So we've developed a document called the 37 crash scenarios, which if you look at all our crash databases, both fatalities and just crashes, you can break them up into 37 crash scenarios and then find the first harmful event. And then from that, does this or any other technology help solve that particular problem? So from that, we're putting together crash description templates for the priority problems. And then we'll use those to develop objective test procedures to test the applications that get developed by the automotive community. The second track is interoperability, and this is the most critical part of the program. Basically, at the highest level, we need to make sure that the Ford-equipped vehicles talk to the Chevy or the Mercedes-equipped vehicles. But as you all know, and I saw there are a lot of papers very related to this area in this week's conference, it's much more complicated than that. We have to have the standards in place for the message sets, security, and the other issues. This is where we're looking at power levels, scalability, and other issues. We have working prototype DSRC units. We've demonstrated them from one manufacturer. Now we need to move that to multiple manufacturers so we can actually demonstrate that we have interoperability across the automotive system. The benefits assessment. This is important specifically to NHTSA for our cost-benefit analysis. This is where we have to create the data to demonstrate that the safety applications actually do reduce crashes, fatalities, and injuries. And so at this point, from the NHTSA perspective, we assume the interoperability is working, and then do you get the safety benefit out of the application? So from this, we'll be using the applications that get developed by the automobile manufacturers and doing field operational testing and objective testing to identify their effectiveness. And then the next one is the application development, and this is where we get those applications that we use for benefit assessment. Here we are relying on the automotive manufacturers to bring us these applications. The big difference between our earlier work, which was focused on driver situational awareness and crash warning, we're now pushing into collision avoidance. And there's some there's some concern here that can you do this solely based on vehicle communications? I think some, if not many, of the manufacturers would prefer to still use vehicle-based sensors to support this, and that's part of what will come out of this, this analysis. Can you do it just with vehicle-based communications, or do you need the additional sensors to get the reliability? And then driver issues. This affects effectiveness, particularly. As you may develop a great application, it may be interoperable, but if you can't communicate to the driver in time or in an effective manner, one, the driver may not find it acceptable, so he'll want to turn it off, or he may react incorrectly. So this is specifically looking at crash avoidance and crash worthiness applications, and how do you communicate to the driver so that they operate the system appropriately. I think a critical issue here at this point, we do not expect to regulate the driver-vehicle interface. We have not been able to create the data that justifies that everyone must do the driver-vehicle interface the same way. So at this point, I expect we will leave that open to each vehicle manufacturer to implement their particular interface within some guidance of, basically threshold times of when they should trigger. And then finally, the policy issues. As an engineer, this gets into issues that are, they're not black and white, they're gray, and they are, it brings in a lot more players than we're used to dealing with. But some of the key issues are, how do we get value to the early adopters? Do we need to encourage retrofit or aftermarket devices? Security and privacy. In interoperability track, we're looking at how do you develop a security solution. But in this work, we're looking at how do you develop a security solution that's acceptable to the American public. You balance, basically you have to balance security versus privacy. And this is where we'll be looking at that. 5.9 gigahertz DSRC enforcement. How do we enforce the system? How do we enforce that it's only being used for the application specified and that it's not being misused? Business models, and government's not really good at business models, as you would expect, but we're creating capability outside of the vehicle. So the DSRC unit on board you'll pay for when you buy your car. How do we sustain all these other activities that have to implement the security and interoperability? How do we ensure that that's maintained? And that would require some type of governance structure. Is that NHTSA? Some other entity in the government? Is it a nonprofit association, or it could be an organization created specifically for this? So so we have to weigh the technical versus policy interactions. That's just the point of that slide. So there's a few issues, sort of the big issues that we're still wrestling with. We've got work in place with our partners in the private industry to address all of these, and that's the penetration versus effectiveness. At what level are we starting to see benefits before we get 100% effectiveness? Will drivers accept this? How do we ensure data security? Can we implement the positioning solution that we require across the entire United States in urban canyons, in different geographic areas? What happens when we scale up the system from a dozen test beds to every vehicle in Manhattan? And is channel switching still required? The original DSRC system had about 10 channels, had a control channel, and you could bounce around to different channels. But for these safety applications, do we want you to just sit on a safety channel all the time? We're trying to determine if that's required. And then policy, we've got the work getting underway with the vehicle manufacturers and the other partners, looking at the trade-offs. How do you operate the system? How do you ensure compliance and enforcement? So when we laid out the V2V research plan, we tried to constrain the scope of it, but we saw really to get acceptance and confidence in this system, in the solution that was developed, we needed to do a safety pilot. So this basically has two objectives. One, to demonstrate the solution, both the applications and the interoperability solutions that get developed in the real-world environment. So this is a model deployment of how we think it'll operate. And secondly, to get driver acceptance. So far, the number of drivers who have seen these systems is very limited, and really we want to increase that manyfold by getting a lot of drivers the opportunity to operate these vehicles with these advanced safety systems. And secondly, this will create an environment for the mobility and environmental folks to be able to develop and test their applications in an effective environment. So the safety pilot has two parts. It'll be a set of driver clinics where we'll take about a couple of dozen vehicles around different parts of the United States to look at it in different geographic areas with different demographic groups and let them test, let the public operate the vehicles under controlled test conditions so they can see how the systems operate. And out of this, we'll get widespread data, which we've just never had before. And then the second part, which will begin in late 2011, would be the actual model deployment. In this, we will take about 2,000 to 3,000 vehicles equipped with basically just the DSRC unit, which is broadcasting, here I am, and that will enable a limited fleet of 50 to 60 vehicles that are completely equipped with the integrated active safety systems to operate in a saturated environment so that they can actually operate their active safety systems. And this will give us data on the effectiveness of the applications and do things like the security implementation. Does it actually operate correctly as planned? And that feeds into our regulatory decision, which will come in 2013. And that's just the roadmap of the timing. So the driver clinics will start in the middle of next year, and then the model deployment ramps up around the beginning of the fourth quarter. So just to wrap up, as I said, we're not just the state of the art anymore. The issues that you guys have been working on are getting implemented. We're seeing them on the vehicles that are on the market that people can actually purchase today. The areas that I think this will move into the future and that we'll have a lot of pressure to work on are integrated safety systems. How do we not just have a bunch of individual applications, but how do they fit together? How do they fit together with the pneumatic devices that the driver wants to bring into the vehicle? Do we carry cooperative and vehicle-based safety systems forward? As I said, the pneumatic devices. And we're evolving. We had situational awareness, crash warning. We're moving into crash avoidance right now. And then will we take the next step? Will there be a big enough pull from the public to actually want vehicle automation? So with that, I thank you.